In the last video, we looked at the special case where the quadratic equation had either a maximum or minimum that lied on the x or y axes. We're going to look at a little more general case when we have intersections at the axes, but it may not be the maximum or minimum. And we're going to look at how to identify them, how to identify from an equation whether we have intersection points and where those intersection points will be. Now we're going to start by looking at the y-axis. We're going to start looking at the y-axis because it has only one case. It has the case that any quadratic equation of this form will exactly intersect the y-axis at one and only one point. That's not true for the x-axis, but that is true for the y-axis. So that's easier one to look at. If you remember when we're looking at maximum or minimums that intersect that y-axis, we could just say that the maximum or minimum point was equal to the constant c, or that value c. Something similar happens here. But first, why does it only intersect at one point? Well, the quadratic of this form is either a U shape in the vertical pointing up or pointing down. So it's either in this direction or upwards, right? So there will only be opportunity for one intersection point. Whereas at any y value, there could be two x points, right? Any x value, there is always only one point associated with it. So that's why there's only one point that will intersect this y-axis. So here are the equations that correspond to this graph here. I just had this as 1x squared plus some bx plus c. And I just varied the b and c terms. And basically you're taking the x squared graph and just shifting it left, right, and in the vertical direction. Okay, so if we were trying to determine what point this line, the quadratic equations intersect the y-axis, we can use the same logic as what we did when we're looking at the maximum. Now, it's not going to occur at max or min necessarily, right? It's shifted from it. But if you plug in x equals 0, which is where the y-axis is, all the a and b terms will all drop out. And then y will just be equal to the c value. So the red graph here intersects at 1, 2, at point 2, which is equal to c. The blue graph intersects at point 1, which is equal to c. The green graph doesn't have a c value, or c value is equal to 0, so it crosses the origin. The black graph intersects at -1, which is again c. So when we're looking at a quadratic equation, we can immediately know where we cross the y-axis by just looking at my c value. Now remember, that doesn't mean that that's the max or min necessarily, but we know that that's where the intersection happens. And we'll find that when we look at applications where the quadratic intersects the axes can have a lot of physical meaning as well. And we'll explore what those cases might be in future videos. So we just explored intersections of a y-axis, and we said that the quadratic equation always intersects the y-axis at one and exactly one point. The x-axis has three different cases. It can intersect the quadratic equation can intersect the x-axis at no points at all, 1 point only, and it could also intersect at 2 points, right? These are three different cases depending on the equation that you have. So it's important to be able to distinguish which case you're looking at just by looking at your equation. So let's take a look. How can we have no points intersect the x-axis? Try to visualize in your mind what that graph might look like. So these are the different cases that we can have, right? So if you're above the x-axis, so it's in the positive y section, all your values are going to be positive. So you're going to have a minimum point that is a positive y value, has a positive y value. Whether it be negative or positive x, that has a negative or positive x value, doesn't matter. It just has a positive y value. So if it has a minimum that's positive y value, it's never going to intersect the x-axis, which makes sense. Conversely, if it has a maximum below the x-axis or a negative y value, then it will never intersect the x-axis either, right? So this video is specifically looking at when we identify points that intersect the x or y axis. So we're not going to look at this case right now in this video, but we will look at this case in the next video. We'll look at how to identify using the equation itself. If we weren't able to visualize the graph, can we just look at the numerical A, B, and C values and determine whether or not we're going to have an intersection? So we'll look at that in the next video. Case 2, the second case where we have one point of intersection, can you visualize what that would look like? One point only intersects this x-axis. All right, so it's a case that we just looked at, right? So it's a case where we have either a minimum or a maximum right on the x-axis. And so we looked at cases that are very similar to this in the previous video. So we're not going to look at this case specifically. We will go over concepts that discuss it, but we're specifically looking at multiple points of intersection. All right, so now we're going to look at the final case where we have 2 points of intersection. Can you visualize what that graph would look like? All right, so this is the more general graph, where we have multiple points of intersection showing up here. So this is the case that we're going to look at in this video. How do we identify, looking at the equations, where these points of intersection will be, or if we're told where the points of intersection are, can we use that information to develop our equations? So we're going to take a look at these 2 cases, or these 2 different types of problems. All right, so we're going to take a look at 2 points of intersection on the x-axis. So here's our first equation example, x squared minus 4x plus 3. I'm keeping the constant out of the a value, or just putting 1 for a for all these examples just to keep things simple. But you know, when we're looking at applications, we can look at it. It changes things slightly, but the concepts are still the same. All right, so let's take a look at a graph first. So I know we're going to talk about the x-axis, but we can, you know, with these examples also look at the y-axis like we saw it before. So this graph, or this line, intersects the y-axis at 123.3, which is equal to the c value, which is consistent with what we talked about earlier in this video. All right, and then we have an x axis intersection at x equals 1 and x equals 3. So looking at this, how can we make sense of the x-axis intersection? Well, I'm going to generalize this equation here, and we're going to define this equation as x minus d times x minus e, where d and e are arbitrary constants that somehow incorporate a, b, and c, and we'll see what that looks like in a second. Right? I can multiply these 2 terms, and then we'll get x squared times, or minus xe minus dx, or minus d plus e times x, plus negative d times negative e, which is positive de. Right, so this is an expansion of this form. In this case, we could say that a equals 1, the way I've set it up here, b is equal to negative d plus e, and c equals d times e. Well, if that's the case here, can we rewrite this equation in this form? Why would we want to do that? Well, in this form, we can easily see the x-axis intersection points. Because if I just look at this, the second equation right here, if I plug in y equals 0, then I can see the special case when x minus d is equal to 0, and the separate case where x minus e is equal to 0. So if y equals 0 and x, then x is equal to d, or x is equal to e, right? Which are the points of intersection. This is essentially the same thing as what we looked at in the previous video. But in the previous video, we had one point of intersection because it was a max or a min point. And in that case, it was of the form x minus d times x minus d, or x minus d squared, right? So it's the same exact concept. It just so happened that it was at a minimum or maximum point. Now we're generalizing it, and we're going to say that d and e don't need to be the same. They could be the same, but they don't have to be. So how can I rewrite this equation so that I can look at it in this form and I quickly identify my points of intersection? Well, this can be rewritten as x minus 3 times x minus 1, right? Because that's x squared minus 3 minus 1 is negative 4x. Minus 3 times negative 1 is positive 3. So that's consistent. So let's take a look at a couple more examples with that same concept in mind. X squared plus 4x plus 3. I have a y-intercept of 3 again. And then can you rewrite this equation so that you can identify x equals negative 1 and x equals negative 3 as points of intersection? Well, similar concept. X plus 3 times x plus 1 is the same equation. So if I plug in a negative 3 here, this term will go to 0. So that will be an x-intercept. If I plug in negative 1 here, this term will go to 0. So y would be equal to 0. So that will be an x-axis intersect. All right, so you see the pattern that we're looking at here. Now, this may not always be be easily done. We may not be able to do this. If we're not able to do this with real numbers and we have to use imaginary numbers, then that's the case when we're out here. We have if I shift this minimum point somewhere in this quadrant here, then you will never hit the x-axis. And so that's the type of case that we're going to look at in the next video. Let's take a look at another example. Right? So into this case, I have a c value of 16, so I intersect x16. I have a negative value here. So this case looks a little different because it doesn't look like this case at all. But I think we talked about this in the previous video as well. Let's take this equation, just put a negative sign in front of it, and then we expand. So then I'll have a negative x squared instead of a positive x squared. I'll have a plus d plus e instead of a minus d plus ex. And then I'll have a minus d instead of a plus d. Other than that, I can have the same form. So you can look at this equation. You see a negative on the a constant value. Factor out the negative for the entire section. Just look at this as a negative times x squared minus 16, and then factor that x squared minus 16 term into a form like this. Well, I can factor it as x minus 4 times x plus 4. You probably have thought about this as like a minus b times a plus b equals a squared minus b squared form, right? Probably in your algebra class. Same exact concept here. And so what would that give me? That would give me a intersect at positive 4 and intersect at negative 4. So it's kind of off camera here, but this is at positive 4 and at negative 4. And then if I write negative x squared plus 4, I can similarly factor out that negative and look at this as x squared minus 4. And then my points of intersection will be plus or minus 2. Right? If I remove this negative value here, and I wrote this equation as x squared minus 4, can you visualize what that graph would look like and what points of intersection you would have? Right? It would be kind of flipped. This positive 4 y-intersect would go down to a negative 4 intersect. And then these x-axis intersection of plus or minus 2 would still be there too, right? So if I change this to a plus x squared minus 4, it would be mirrored in that way. So it's useful to visualize how a graph would shift with certain pattern of changes, right? So recognizing that can help us understand what graphically is going on a mathematical basis. But from our perspective, even more importantly, what's going to happen on a physical level if we give the x and y axes and some physical meaning, right? I'll give it a time component, give it a voltage component, give it a force component, And so we'll look at those when we look at different applications. All right, so just like in the last video, I want you to press pause, take a look at this slide, and see if you can solve these 7 problems, right? So for the graphs, I've identified the points of intersection, right? So for this graph, I have point of intersection at -5 and +5. This one at -7 and -4, and so forth. And then I have equations for 3 graphs that I don't have. So I want you, for these 3 equations, first identify how you can factor the equations in a polynomial form that we showed earlier, and then use that to identify the points of intersection of your x-axes, and then see if you can graph them, right? So remember in the back of your mind what a positive or a negative a value, or in this case positive or negative 1 value, would tell you about the max or min. So press pause. I'll give you a second to press pause. Work on it for a couple minutes or however long you need, and then press play. It's very useful to solve problems without being given the answer first. Even if you get it wrong, that's struggling through the problem and figuring out where your sticking points are is really important. It's oftentimes really easy to watch a video or listen to someone explain a concept. All right, that makes sense, that makes sense, that makes sense. But then when you have a blank sheet in front of you, be able to solve it on your own sometimes can be a different story. So, let yourself go through the struggle if you're still working through this, or this is the first time you're seeing this, and then come back and look at the video if you're really stuck, to see what concepts you may have missed. All right, so press pause, and now I'm going to show you what the answers are for each of these. All right, so we have plus or minus 5, so this is going to be like the a minus b times a plus b kind of form, right? And then we have another case like that, right? This x squared minus 4 is of the similar case. It's basically the flip case of the previous slide that we looked at. All right, so hopefully this makes sense. We're going to look at, in the next video, the case where we don't have any intersection points, and look at how do we determine that that is the case just by looking at the equations.